Hi everyone, and thanks for coming to our talk where you should fear your mundane office equipment, where we're going to present our enterprise printer research, and thanks also to Hacking the Box for giving us this great opportunity. Yeah, first of all, just a brief introduction about who we are. This is Mario Rivas, and I'm Daniel Romero, both work as security consultants and researchers at NCC Group in the Madrid office. Here you have, for example, some interests or Twitter accounts, emails, etc. But if you want to know what's better, we always have for a beer, so just let us know and we can take a beer. Well, this is the agenda of our talk. This is a really classical agenda where we'll start with a brief introduction and the attack surface that we have covered during our research. Mario will present the testimology and some facets that we have developed during our research and a way across the different vulnerabilities that we have found. After that, we will show you some exploits and the difficulties that we came across, okay? And finally, just a brief conclusions. Okay, let's go with the introduction. Okay, the main goal of the research was testing enterprise devices, okay, and figure out the current state of security of them. So we thought that printers would be a good target. So we select 6 medium-sized enterprise printers, and we decided to focus this research on our red teaming approach. So the outcomes of the research could be used during our red teaming engagement, for example. So we did vulnerability research, exploitation, and post-exploitation, okay? Keep in mind that it's not an assessment, so we don't need to find all the vulnerabilities that the printer have. So we only need to find one vulnerability that provides us remote code execution, okay? But why printers? These are really good questions. Printers have been well extended in companies since many years ago, and usually they are connected to different networks, to different VLANs, and for example, you can use them in order to pivoting, so different department attack the different department. Obviously, the information which is managed by a printer are really sensitive. We have, for example, corporate, personal, financial, customer, etc., etc. But don't forget the information included within the configuration, where, for example, we can find domain accounts, password credentials, etc. So it's really sensitive information. Usually, printers are also considered low-risk targets, so probably they are not configured securely or properly by the IT department. So at the end, we have uncontrolled devices, managing really sensitive information, and connected to the most of the printer company's network, sorry. So this is an example of some weeks ago where Microsoft captured Russian state hackers using printers in order to attack different companies, okay? And why not? Some vendors decided to make statements like this one, so it seems like a challenge for us. Let's go with the attack surface. Well, first comment that we identified 2 different operating systems within our printers. The first one is a real-time operation system, and the next one is a Linux, okay? And obviously, they have many attack surfaces, like web applications and web servers, mobile application, file parsers, updates and firmwares, printer languages, external services like, for example, Google Cloud Print or AirPrint, management services and others like Telnet, SNMP, etc., and proximity attacks like Wi-Fi, USB, NFC, etc., etc. Okay, and we also decided to include 2 other tasks for this attack surface, like hardware analysis and post-exploitation. Okay, but obviously we didn't have enough time to cover all these attack surface because it's really huge. And finally, we decided to cover the following ones. Okay, those painted in gray because we didn't include these tests in all the printers. This is another picture about the attack surface, a more detailed picture where you can see the different elements that we include within each part of the attack surface. Where, for example, within the printer language and file format, we decided to include the PGL, the PCL, and PS languages. Okay, let's go with the test methodology and fasting.
Okay, so this is the main methodology that we followed during the research. We started with the state-of-the-art and setting up our printers. Then we chose some scope of the attack surface, as we just saw, and then in a cycling process, we started searching for vulnerabilities, fuzzing different protocols and finding some crashes, then analyzing them, and then trying to exploit them in order to compromise the device or gain additional knowledge. All this while also analyzing the firmware in the cases we had it, and also analyzing the hardware to get some useful information, as we will see later. Talking about fuzzing, we started with dumb fuzzers, which are really quick to launch, and we continued with the smarter ones, which require more time but give better results. Actually, both techniques gave out great results, but also we felt that it was harder and more time consuming than it should be. So we decided to make another fuzzer. While looking at the state of the art, we found two amazing tools, very well known, Sally and Bufas, both with great functionalities and a lot of the things that we needed, but we were changing a lot of the code, so we decided to fork Bufas, and we ended up creating a different monster. And after Sally and Boo, Mike Wazowski will be the next one, so we call this Fazowski. We wrote it in Python 3, and we improved some modules like the string fuzzing libraries, and we made fuzzer modules to keep all our protocol fuzzers under a single program with a similar behavior. Between the rest of the changes, we wanted to solve the different difficulties that we were having while fuzzing. The first one will be that different implementations of the same protocol behave different. And when a device crashes, sometimes it can go totally down, or maybe a service stop answering, or maybe just print an stack trace in some debug interface. So for that, we wanted to give flexibility, and we made the main program with a lot of arguments to control the fuzzing session, and we made monitor modules to constantly check the target. Then, when a device crashes, sometimes we needed to reboot it manually. So for that, we made restarted modules to do, for example, to turn off and on a smart plug. And then to give usability to our fuzzer, we made a nice console where we can pause and control the fuzzing session and do some things like retest any test case, or do some other things like print in human readable format and the test cases that we are sending, and save standalone scripts that we can send later to the manufacturers maybe, or just use it while developing an exploit. So let's see a very quick demo. It's a bit cut, I think. Okay, perfect. I will detect the way. So we have below a ping to our target, and you can see there a lot of the options that we have. We have also our fuzzer modules that we have developed, the restarted modules and the monitored modules, and other options. And we are now going to launch our fuzzer to our target, the printer one, in the 631 port, using the Internet Printing Protocol fuzzer, IPP, and the get printer attributes part of that protocol. And we are going to use a restarted module that turns off and on a smart plug that we have connected to a printer. We have here the console or cool logo and some of the commands that we have implemented. We are now going to test the connection to a target, sending a non-fuzz packet. And after receiving some information from that request, we can go to a different test case and continue the execution from there for brevity. So now we are continuing, and you can see some of the test cases like in a very similar way to Bufas. And after sending a pair of them, you will see below that we will stop receiving ICMPs. There it is. And now we have detected that in the fuzzer, and we are going to restart the target using the smart plug module. And after that, we will wait for the target to recover, and it will continue the execution automatically, getting more crashes and saving some suspects. But we don't want to do that. We can Control-C and go to the console, check the suspects we have, the 501 in this case, and we can print it in a human readable format, where you can see in the longest line that we are sending 10,000 Cs in this case, instead of the default value EN, that was the mutant of the packet. We can also print this like with a proof of concept code that we can copy and paste into a script and send it to the manufacturer as a proof of concept, or just use it later while developing an exploit. Now we are going to wait for it to recover, and we are going to retest if this test case was crashing the device or it was crashed by any other thing that we didn't know. So for that, we can use the fast command with the 501 test case in this case. And as you will see, we stop receiving ICMPs again. We have a crash, a bug. In this case was a heap buffer overflow, and we can save this proof of concept into a file for later use. And we can also disable the element, as we may not want to continue testing this because it's already vulnerable and we already know it, so why wasting time in that? So that was this demo. Okay, all the code is already available in our external GitHub, and check it out and follow it because there are a lot of changes coming soon. And let's go for just a bit of hardware. We took a very basic approach, mainly searching for things that will allow us with the exploitation of the printer. For example, the bug interfaces like UART or JTAG, or some other things that may allow us to dump the firmware or get some useful information. And while doing that, we were also having too much fun, and we did some things that we shouldn't, and now one of the printers is not going to print anymore. Let's just say kill a printer, save a tree. So one of the first things we did was looking for exposed memories. Like in this example, we use a bus pirate to, through the SPI protocol, download the firmware from one of the devices. And we also found some serial ports in 3 of the 6 printers tested. And we also found some JTAG ports that seem to be disabled. The serial ports were extremely useful as they gave us a lot of information like the bug, errors, and stack traces. And were really useful to exploit some of the vulnerabilities that we found. Also, one of them was especially interesting as it gave us an interactive shell that we could use to read, write, and execute things in the memory of the device. So we use this for a hardware backdoor, which could be implanted by someone with physical access to a printer in 2 or 3 minutes. And for this, we use a Raspberry Pi that you can see in the picture, which was connected to the serial board and was also powered by it. So whenever the printer is on, the Raspberry Pi will be on. And the Raspberry Pi will be connected to a Wi-Fi access point, and from there we could have all these capabilities. So let's see a second demo. Very quick also. Okay, you're on our PC where the Raspberry Pi is connected, and we can SSH to it. And from here we have a direct access to our serial port of the printer. So we can just go into the console. We are now in the console, and we can, for example, print the shell where there are a lot of commands to read, write, and execute things. And we can do some things, for example, to dump some memory, as you can see. But this is not a very nice format, so we are now going to show you this with a little script that we did to dump some of the secrets. We can use the script with specifying the serial port and the baud rate, and after launching it, you can see some of the secrets, like for example, the administrator password, which was Lala in this case, then a null byte, and then something that is the part of the previous password that was not overwritten while setting a shorter one. And of course, all the secrets in the printer are in clear test because we are like in the year 2000 yet or something. So that was a quick demo. We didn't execute things here, but we have an exploit where we will show you that with a remote code execution. Okay, so after this quick hardware, we are going to see some of the common flaws found. Just a quick overview. We have a lot of well, you can see the red means high or critical risk, yellow means medium risk ones, and the skull means that we use some vulnerabilities to execute code in the device. So, starting with the web applications, we found really weak default configurations, exposing almost all services available, also exposing, well, actually more than 20 in some cases, also exposing the management panel with default or without credentials, and basically reminding us the security of products of 20 years ago. And we found all the typical web application issues like cross-site request forgery, lack of access controls in different functionalities, for example, to do a full backup of the configuration of the device, and some cross-site scripting issues like 1, 2, 3, and 4, and also a path traversal in one of the Linux printers that unfortunately allowed us only to obtain some specific extensions, and we were not able to further exploit this to get closer to our objective, which was to get full control of the device. So all these issues are not bad, but we are looking for something that may allow us to get full control of the device. So looking at the frameworks, we found a slightly few more interesting functionalities, like this one, where you can see we got a lot of information, including authorization and security logs, including session, cookies, Active Directory logs, Kerberos logs, more information like the full list of processes or other information about the underlying operating system. In this second one was very similar to the first one, with different functionalities under different URLs. And this was used in one of the exploits that we will explain in a few minutes. And this third one was even better because it just allowed us to download the full memory of the device, why not, and get all the secrets and anything that was in the memory at that time, like passwords, documents, whatever. So all of this was accessible without any kind of authentication because it's hidden features. And, well, going to the memory corruption issues, we found a lot, too many, more than we could handle or investigate. So in a lot of the services that the printer had, like not only the web application, but also in printer services like IPP or LPD or the Google Cloud Print implementation, SNMP, basically we stopped searching these kind of vulnerabilities because we had a lot. Basically we had vulnerabilities everywhere, which led to crashes everywhere and some very useful stack traces, this one in one of the serial ports, where we overwritten the PC, and this is from another exploit that we won't see today, but don't worry now, Dan is going to explain you two other ones.
Yeah. Okay, let's go with a couple of exploit examples developed during our research. This is the first one. This is the easy case, and this bug was found by one of web application faucets, as you can see within the image. After sending a HTTP request, a crafted HTTP request with a really long cookie value, the printer will crash. So probably this is a basic static stack buffer overflow. Okay. Looking to the framework, we identified that developers, for example, forgot to include boundary checks in the code. So probably the string copy, which is copying the cookie value into a stack array, could leak a buffer overflow. Okay. And another important point here is the count variable. The count variable is the cookie size, including the cookie name, the equal symbol, and the cookie value, okay? And it is used, for example, within the string copy size argument, where 15 bytes were subtracted from this count variable, okay? And question here will be, do you really think that there is only one bug here? Obviously, no. Imagine that we replace the equal symbol by a semicolon symbol, okay? The count variable will result in 14 bytes. And 14 minus 15 is a negative number. So we are copying a really huge space memory into a stack array. So we have two vulnerabilities in the same line. These are two proof of concept. The first one is just sending a really long cookie value, and the second one just replacing the equal symbol by the semicolon symbol. Okay. And thinking about exploitation, looks like that we are going back to the 90s exploit with printers, so which is really scarce. Let's go with to check the difficulties. We identify SLR within the heap and the stack. We didn't have software and hardware debug, and keep in mind that we are trying to attack RTOS, so we don't have a shell here. Okay, we need to reverse engineer the framework in order to identify some potential functions and functionalities that we can use within our shell code, for example. Okay. Helpers, obviously we have direct PC overwritten, we have potential, read, write, and executable memory in the whole memory probably. So we have the stack executable. Okay, and as Mario commented before, we also identify a really useful vulnerability in this printer that allow us to print get the printer's memory. So we can use this vulnerability in order to bypass the SLR, for example. Okay, so the exploitation change will be: we're going to send a shellcode to the printer just between patterns. We're going to dump using the memory functionality, the memory hiding functionality, the RAM. We're going to try to identify our shellcode within the memory. We're going to try to trigger the buffer overflow, and finally we're going to jump into the shellcode. Okay. But for our red teaming tools, we wanted something more, and question here will be, what is one of the most important data managed by a printer? Obviously, the documents. Okay, so why don't create a shellcode that prints, that hooks the print functionality, steal all data or documents into the printer, and send them through a reverse connection, for example. Okay, so let's go with the demo. For this demo, we are going to have two different machines. The first one is the attacker machine that will execute exploit, and an exploit handler that will receive all the information from the printer, and the second machine will be a victim machine that will send the document to the printer. On the right side, you can also see the hacked printer. Okay. Let me open this one, the demo. Okay, this is the demo. Here you have the attacker machine, which this is the IP address for the attacker machine. And below you can see the exploit for this printer, okay? Where we need three different arguments: the target IP, the target port, and the reverse IP. We're going to attack the printer one in the port 18, and we're going to here include the attacker machine, which is the reverse IP that we want to receive the connection. And but before that, we're going to execute our exploit handler that we will receive all data, including sending from the printer. Okay, this is listening the port 1337. And below, we are going to execute our exploit. As you can see in the exploit, in the third line, we're using our memory leak in order to identify our shellcode in the memory. And after that, we were able to receive a connection from our printer with the sentence hack the planet frame, which was included within the shellcode, for example. This is the victim machine, which is a different IP address. And what we are going to do now is just sending this document to the printer. Okay, we're going to select exactly the same printer, which is the printer one. And after sending the document, you can see how the exploit handler is receiving some data. This is the data that the printer sends to our exploit handler, and we are now converting this data into a PDF. Okay, so after some seconds after that, here you go. This is the document that we were able to steal from the printer, okay? And the printer still continues printing normally, and our exploit handler also implemented a new functionality that forward this document to another printer controlled by the attacker, okay? This was the demo. Let's go with sorry. Oh, sorry. This was the first. It was the easy case, and let's go with the tricky case. Okay. For this exploit, we didn't have software and hardware debug, and we came across another difficulties and protection that we will see now. So it is not going to be easy to explain, but we will try it. So be patient, please. Okay. This is the vulnerability. We identify the vulnerability in the same place as the previous one, but for this case, we have two different paths within the cookie. Okay, the first path is something like a hash and separated by a column. We have something like a base 64 string. Okay, And reverse engineering the framework, we identify some potential functionalities that could contain the vulnerability. But the most important function here was the function that they called the base60 code string. Okay. And we started analyzing this function, the base64 function, the code function, and we identified that extract was passed as argument to this function, okay? And this extract has different elements, for example, the source pointer, which is the base64 cookie string, okay? The destination pointer that will be filled within this function with the result of the base64 cookie, and for example, the source len and the destination len. But this function, the base64 function, was called by the code in the highlighted area. You can see here, we are calling the basis for the code function, and we are passing a cookie, a struct cookie, as argument. Okay, and the buffer flow occurs because the destination pointer, the struct destination pointer, was directly associated to a stack array. So if we send a really long cookie value base64 encode, we are smashing the stack. We are directly overflowing the stack array. So, but the problem here is that was analyzed locally. We need to corroborate this dynamically. Okay, so we decided to use the Unicorn framework, which allows you to emulate some piece of code that see the result, for example, like the registers, and we create a script that emulate different functions. For example, the function that get and check the second part of the cookie, the string len, the base64 return, and other functions. Okay, and we create a script, and we passed 108 base64 encode as argument. Okay, and after execute our script, we were able here. We can see here how we were able to override the PC register. For example, we can also control all data within the stack pointer, and we were able also to override the R4 and R5 registers. This is because the last instruction executed before triggering the buffer flow is a pop instruction, which is popping the R4, R5, and PC registers. Okay, so we have now all what we need in order to create our exploit. But when we started to do this, everything became inside here. So for example, we detect that the stack was not executable. We tried to use many firmware addresses in order to create order of change or shellcode, but none of them worked properly because they were using something like ASLR, or the RTO was using something like ASLR. And we also identified that they were using a modified T-kernel version. Okay, so the most important point here is it is a non-monolithic operation system, and different tasks could be executed at the same time. So probably what the kernel is doing is just taking some code from the framework and execute this code in the memory in a different address. So this is the reason because we weren't able to use firmware addresses in order to create our shell code, for example. Probably they were applying an offset or something like that. Okay. Therefore, we didn't know where and how our shell code can be executed because we have something like SLR on an NX, and we were able to find valid addresses to create our rope change. But we need gadgets in order to create our rope change. So we need to find a way in order to find these rope gadgets, okay? And thinking about this, we identified some insane protection and approaches, for example, reverse engineering the T-kernel structure, but obviously we didn't have enough time to do this because it could take weeks or months. Reverse engineering the bootloader in order to find some potential static addresses, which is a good option. Identify static memory like configurations, okay, within the printers, but obviously we don't know what permission is associated in the kernel to that part of code, okay, or memory. But forcing random addresses that we'll see now and looking for code helpers, okay? Code helpers like this is an infinite loop that we found within the bootloader, okay? So when we came across with this piece of code, we thought that a good option would be create a blind exploitation, okay? Let me explain you. imagine that we have a code that we don't know if this code was executed properly or not within the memory. What we can do is, after that code, we're going to try to jump into our infinite loop. If the printer remains up, that means that the code was executed properly. If the printer crashes, that means that the code was not executed properly because the infinite loop was not executed. So we can do something like a blind SQL injection, but with memory corruptions. Okay, and we finally decided to mix the code helper with the approach of brute forcing the PC register and figure out what instruction was executed in memory. The main goal with this approach is helping us with the infinite loop. We're going to try to guess exactly what instruction was executed in memory. Let's go with an example. Remember that we can control the PC register and all data, including with the stack pointer. So for this example, we're going to include 3 sets of A's, and after that, the infinite loop address. And we're going to start to brute forcing the printer's memory with some addresses. And finally, we jump into the address 14, which is a pop instruction, but we don't know whether this is a pop instruction. We are going to try to guess that this is a pop instruction. And after execute the pop instruction, we can see how our R0 register was overwritten by the first set of A's with this one, and the PC register was overwritten by the second set of A's. So the printer will crash, the printer will be down. In order to solve this problem and exactly guess what instruction was executed in memory, what we can do is change the information, including with this stack pointer. We're going to change this information, and we're going to include only one set of A's, and after that, the infinite loop, for example. And if we execute this exactly same address, our R0 register will be overwritten by the first set of A's, but the PC register will be overwritten by the infinite loop address. So the printer will remain up. So just changing the information included with the stack pointer, we can see we were able to guess that the instruction that was executed in memory was a pop instruction, which is popping one register. We don't know which one, and after that, the PC register. So using this methodology or approach, we were able to identify 3 different instructions in memory. The first one in the address 12, which is an add instruction. The next one is in the address 14, which is a pop instruction. And in the distance of 500 bytes, we identify another pop instruction. So we have now a pattern. Keep in mind that this was in memory, So we have now a pattern, exactly a pattern in memory with 3, where we were able to identify 3 instructions, The goal here was try to identify the exactly same pattern that we found in memory in our firmware address, in firmware data. And we were able to identify the exactly pattern, but in another address. What that means is that the kernel is applying an offset. When the kernel is taking this code and execute this code in memory, the kernel is applying an offset. But we know now what exactly offset was applied by the kernel. So this provides us useful rope gadgets and potential helpers in order to continue with the execution flow, for example. Sorry for this, but this is the way that we follow in order to create or exploit. But this was not enough. We need more rope gadgets in order to create or exploit. And at this moment, we remember that we identify another interesting issue or vulnerability within this printer that provides us where exactly images and GIFs were allocated in memory. So we can use this memory leak vulnerability in order to bypass, for example, the ASLR. And why not? We can also use the images and GIFs in order to create all rope gadgets, or rope change. So what we're going to do now is something like exploitation with images. So what we can do here is, for example, download all the web portal images and GIFs to our laptop. We can use, for example, the rope gadget Python script in order to find some interesting instructions within the images and GIFs. Obviously, images and GIFs are no code. So we are not going to find coherent instructions within the image, but they are bytes. But probably we can find some interesting instructions within them. We did that, and we finally were able to identify some useful instruction and grub gadgets in order to create our shellcode. Okay, but we came across with another problem, the caches. This is the last problem, I promise you. But obviously we should flash the cache. So we have some action here, for example, call the RM instruction, call to different functions like sleep and protect and others, or continue with the execution flow, which probably is the most harder but the most professional option. Just quickly, in order to continue with the execution flow, we need that our shellcode implement 3 different parts. The first one is our payload. We should do something with our exploit, something like we did in the previous exploit, for example, just hooking the printer functionality and steal all data sent to the printer through our reverse connection. The second part should change the address that we were able to override with the exploit, so with a valid address. At the end, we want to continue with the execution flow, so we need to jump to a valid function, for example, okay? And the third part should align the stack pointer. We have executed our payload, we change the address, so probably we change it our stack pointer. So we need to align the stack pointer to a previous state again, and just finally just trigger the vulnerability as many times as you want, okay? Let's go with the demo for this exploit. Let me open this. This is the demo. For this, keep in mind that for the previous exploit, we attacked the documents. And for this exploit, we are going to attack exactly the printer's memory, okay? So for this exploit, we implement 4 different functionalities. The first one is the write functionality, which allows you to write bytes into the printer's memory and jump into it. For example, if we want to write a shellcode. The next one is write a file, which is the same, but we can, for example, use a local file that you have in your laptop in order to overwrite a file in the printer, like an image, for example. And the next one is the read functionality. This allows you to read in sensitive data from the printer memory. Okay. The next is a search functionality, which is really useful, and it can allow you to, for example, find sensitive information with the printer's memory. Okay. But in order to write, read, etc., we need to copy all data that we want to read, for example, in a known place in order to read them. So what we can do, what we did here is just copy the data that we want to read in a known place. For example, the images. So this is the image that we are going to use to replace to copy the information. This is a classical PNG with a normal header. What we are going to do now is write a sentence into the printer memory. Okay, we can write a shellcode, but for this example, it's just a sentence. Hi everyone. And we are not going to jump into this code because it's not a shellcode. You can see how we are writing the information in a known place, and if we download the image again, you can see how the first line contains our hi everyone sentence, and this is the printer's memory. Okay, we can do the same, but with the write file. For example, functionality in order to write a logo into in order to overwrite a web portal image, for example. Okay. Let's go with this. This is an image from the printer that we can, as you can see here, this is the image and the path, and we're going to copy this path in our exploit. Okay. Let's go with the copy in this. And after that, what we're going to do is just read the logo, and we're going to write this information into the printer memory. Okay, it takes a bit, so let me this forward. I don't know where is it exactly. It takes a bit. Okay, and after 2 seconds, this exploit will finish. This finish, we're going to check the image again. Okay, this is the image that we wanted to overwrite, and if we refresh this image, we were able to overwrite this image with the Hack in the Box logo. Okay. And this was for write information, but another interesting thing is read information from the printer. Okay, so we will also implement another functionality, which is the search functionality, in order to find interesting information within this. So looking into the printer, we identify that this was configured with a domain account. In this case, the entity group, the admin user. but the password is not here in clear test. So we are going to try to find this password within the printer memory and download this. Okay. So we are going to use the search functionality in order to search the entity group text into the printer memory. And after execute this, you can see how we're writing the shellcode that will do the work. And we're downloading the images. As you can see, the entity group text was found in the address, this one. So this is the address the entity group text should be, okay? We're going to now use the read functionality in order to dump this information from this address, okay? This is the read functionality. We're going to copy and paste the same address, and we're going to read 500 bytes. As you can see here, we are reading the information from this address, and we are copying the same information into the image address that we are going to download. Okay, and after finishing, it takes a bit. If we download again the image, you can see, for example, at the bottom, we can see at the below, sorry, how the entity group, user was found, and we can also see how, a little bit below, how the super password was the password that was included within the printer memory, obviously in clear text also. So with this exploit, we were able to write and read sensitive information into the printer memory and control the whole printers, okay? This was the demo for this exploit, and let's go with the conclusions.
Okay, so before that, I hope you are all still alive after Danny trying to explain this last exploit. We knew it was hard. So going to the responsible vulnerability disclosure process, we started it in February, and we got a very mixed response from the different manufacturers. Some had a very mature process for this and were really quick and helpful and releasing patches and everything. And on the other hand, we can just say that sometimes it was easier to find the vulnerabilities than the security department. So I guess they should do some work in that area. Most of them have already published patches for most of the issues, and we have already published advisories for all of them. And going to the CVE party, we got a lot of them, 50 in this case. 14 were medium risk ones, another 14 were high risk ones, and the rest 22 were critical risk ones. We didn't report any low ones. Just take the number per manufacturer. You shouldn't take it as an indicative of their state of security, because some of the vendors grouped different vulnerabilities under the same CVE entries. Just for reference, the full list. And going for the main conclusion, this research aimed to show how the state of security in common office devices, such as printers, which are present in most, if not all organizations, is still very mature and largely ignored. We found a large number of high and critical risk issues in all the printers tested, and we wrote functional exploits to execute remote code in 4 of them. We show here 2, one to retrieve documents and one to retrieve other secrets from the memory. And we ran out of time, so we weren't able to develop more exploits for the other printers, but they have vulnerabilities that could probably lead to that. And we stopped searching for vulnerabilities after finding a few of them, as we said. So we think that probably there are a lot more to be found. And we only checked a few services, as you saw in the attack surface. So there is a lot more to research in this area. And by what we saw, the first one looking at the services will probably find some gold in there. And we do not expect the same manufacturer having different implementations for some of the protocols like IPP or LPD. So probably the number of vulnerabilities, these vulnerabilities affects a huge number of devices, sometimes larger than the number made by the manufacturers. We could also say less marketing and more security. And going for the main conclusion, the recommendation, sorry, for manufacturers, it will be to start investing in security. It's necessary in all the phases of a product development lifecycle. Then for organizations, they should start by considering these devices which are connected to their corporate networks as the threats they are, because they have a lot of vulnerabilities. And for hackers, this is a very mature field. If you start researching embedded devices, starting from the very basics, you are going to find a lot of issues, and you will learn a lot, and you will have a lot of fun, so you should give it a try. And as expected, a quick show and search showed us a lot of these devices connected to internet, and we even saw that some different manufacturers seem to be using the same code for their printer, as you can see in these two images that are quite similar. So probably we tested more vendors than we thought. And acknowledgement finally, thanks to the Madrid office, Matt Lewis and Philip Moss for all their support. Also special thanks to Maribel and Chris for suffering us the most. And also thank you to Álvaro Felipe, who was part of the research during the first days, and also helped us with great ideas during the exploitation phases. So it was difficult to put a lot of months of research into just 45 minutes, but thank you for suffering us.
That's all. Okay. You have any question? Or?
Yeah, we're running a little bit late, but I think we've got time for one question, if anyone has anything.
Hopefully not.
No? Let's take one off the Slido X, perhaps.
We can see it.
We've got here, so I'll just read it out. The top question is, could these vulnerabilities be effectively leveraged to establish command and control on a local network?
Good.
Yes, basically, yes, this, you can totally do that. If you can execute code, you could sometimes modify the firmware or the file system to get persistence, depending of the operating system, and you could totally do that. It's totally feasible.
Yeah, we have a demo that we were able to show in this talk, but we are doing exactly just executing a command control with the printer, just pivoting through our internal network in order to attack the network. So that's exactly the question. Yeah.
Thank you very much. I think we'll have to call it there. So thank you very much, guys.
No problem. Thank you.